We have Euclidean geometry from a November 2023 exam paper. So please take note that there are 3 Euclidean geometry questions within this paper. Question 8, question 9, and question 10. So let us get started with question 8. 8.1. In the diagram, O is the center of the circle. Use the diagram above to prove the theorem which states that the angle subtended by a chord at the center of the circle is equal to twice the angle subtended by the same chord at the circumference. That is, prove that TOP is equal to 2TKP. Now the angle at the center, TOP, is this one over here. The angle at the circumference, TKP, is this one over here. So we need to prove that the angle at the center is double the angle at the circumference. Reason being is that the chord TP subtends both the angle O and K. However, what is important is that the angle O is subtended at the center, whereas the angle K is subtended at the circumference. So when a chord subtends one angle at the center and another angle at the circumference, take note that the angle at the center will always be double the angle at the circumference. That means that if the angle K is 60 degrees, the angle at the center will be double that. It will be 120. Or if the angle at the center is 100 degrees, because the angle at the center is double the angle at the circumference, this angle has to be 50. So that is the main idea behind this theorem. So let us get started. So in order to prove this theorem, I'm going to construct a line that breaks this circle in half, from K passing through to O and then reaching the other side of the circumference. I'm then going to look at the left side and the right side of that constructed line separately, using the exterior angle of a triangle is equal to the sum of the opposite two interior angles of that triangle, and then I'm going to combine them. So let us get started with that. This is question 8.1. Our first step is to construct KO and extend it to the circumference. Now, please take note that when constructing a line, you are going to use a dotted line. So we are going to construct the line KO, and then we are going to extend this line to the other side, or you could say to the circumference. Now, let us break this line up so that it is a dotted line. Now, as you can see, we've now broken this figure up, or we've split the figure in half. From here, I'm going to look at the right and left side independently. So let's start with the right. So I'm going to highlight this triangle that I want you to focus on. So it is the triangle KOP, and it has an exterior angle. So this is the exterior angle of the triangle, and we are going to focus on the opposite two interior angles. Now, something that is very important to take note of is that OK is equal to OP, reason being radii. So let us just put in those markings. So OP is equal to OK radii. Because OP is equal to OK, we then know that the angle P is equal to the angle K, because the angles opposite equal sides are equal. And our reason is just angles opposite equal sides. Now, from here, we are going to create an equation, or you could say we are going to formulate an equation to try and find the angle O, or we can call it O1 instead. Now, from here, before we move any further, let us quickly indicate the different angles. So I'm going to refer to this as O1 and O2, as K1 and K2. So here we are now going to state that the angle O2 is equal to K2 plus the angle P. So here let us say that P is equal to K2, so we'll be a bit more specific. So please take note that the reason this is true is because the exterior angle of the triangle is equal to the opposite interior angle of that triangle. So our reason is exterior angle of triangle equals sum of opposite two interior angles. So I'm just quickly going to copy this equation and then we are going to continue. So here, please take note that it was previously mentioned that the angle P is equal to the angle K2. So because they are equal, I'm going to replace P with K2. So it is going to be the angle O2 is equal to K2 plus K2. We're then going to add up the like terms, giving us O2 as equal to 2 K2. So this is the right side. This is the first part. We're going to do the exact same thing, but with the left side of the triangle this time. So we're going to focus on the left side. Something important to take note of is that OK is equal to OT radii. So on the left triangle, we know that OK is equal to OT, and our reason is radii. We then know that the angle K1 is equal to the angle T, because angles opposite equal sides are equal. So K1 equals T, and our reason is just angles opposite equal sides. From here, we can then state that the angle O1 is equal to the sum of the opposite two interior angles. So we know that O1 is equal to K1 plus T. And our reason is the exterior angle of triangle is equal to the sum of the opposite two interior angles. Now please take note that because K1 is equal to the angle T, we can replace the angle T with the angle K1 in the equation. We can add up like terms, and we have 2 K1. So here we have O1 equal to double K1, and we have O2 equal to double K2. Now, if you remember the original question, we needed to find TOP, not just O1 and O2. So to find TOP, you can clearly see that TOP is made up of O1 and O2. So here we are going to state the angle TOP is equal to the angle O1 plus the angle O2. Now, we know that the angle O1 is equal to 2 times the angle K1, and the angle O2 is equal to 2 times the angle K2. From here, all we are going to do is take out a common factor of 2, and we are left with K1 plus K2. Now, let's go back and have a look. What is the angle K2 and K1 equal to? So you can see that K1 and K2 form the whole of the angle K, or you can call it TKP. So in place of K1 and K2, we are going to put TKP. So take note that K1 plus K2 is equal to, so here we are just going to replace K1 and K2 with TKP, and that is it. We have now proven the theorem that states the angle at the center is equal to the angle at the circumference if they are both subtended by the same chord. So the angle TOP is equal to 2 times the angle TKP, and that is it. Next, let us have a look at 8.2. In the diagram, O is the center of the circle, and ABCD is a cyclic quadrilateral. OB and OD are drawn. So please take note that because ABCD is a cyclic quadrilateral, that means that the opposite angles, or you could say the sum of the opposite angles, are supplementary. So let us highlight this cyclic quad. So here you should be able to see that the angle A plus the angle C is equal to 180. In addition to this, the angle B plus the angle D, or you could say the whole of B and the whole of D, is equal to 180. In addition to this, you should be able to notice the theorem that we previously proved. The angle at the center is 2 times the angle at the circumference if they are both subtended by the same chord. So you can see that the chord DB, or you could say the arc DB, subtends the angle O1 and the angle A. O1 is subtended at the center, A is subtended at the circumference. So we now know that O1 is equal to 2 times the angle A. In addition to this, you should notice angles around a point. O1 plus O2 is equal to 360. Always remember the angles around a point is equal to 360 degrees. Now, the last theorem that you should notice is one that we've previously discussed, but in a different representation. It's a different form of the same theorem. It is the angle at the center, in this particular case, O2, is double the angle at the circumference, in this particular case, angle C. So we know that O2 is equal to 2 times the angle C. So it is still the same theorem as previously proven, it's just a different representation of it. Now that we've identified all the different theorems within the figure, let us have a look at the question. If O1 is equal to 4x plus 100, so we are given the angle O1, and C is equal to x plus 34. Calculate giving reasons the size of x. So please take note that this is for 5 marks. Now, if we want to find x, we have been given O1 and C in terms of x. That means we need to use both O1 and C. So we are going to just identify all of the different theorems that have O1 and C in them. So it is the first one that we discussed, as well as the third one that we discussed, and the fourth one as well. So these three theorems that we've discussed have O1 and C in them. Now, a way that I can see that we can solve for x is by using angle A plus angle C is equal to 180, opposite angles of a cyclic quad. Then we can also create another expression for the angle O1, because keep in mind O1 is equal to double the angle A. Angle at the center, 2 times the angle at the circumference. Now, from here, let us just substitute quickly. So A plus C is x plus 34 equals 180. We can solve for A in terms of x. Then we know that O1 is equal to double A. So we can take the value of O1, which is 4x plus 100. We can substitute A in terms of x, and then x will be the only unknown. And then we can just solve for x from there. So that is the approach that we are going to use. We are going to make use of the theorem that states angle A plus angle C is equal to 180, opposite angles of a cyclic quad. We are going to make use of the theorem that states angle O1 is equal to 2 times angle A, angle at the center, 2 times angle at the circumference. So let us get started. So we are going to start with the first part. So let us just highlight this cyclic quad. So our focus is going to be on the angle A and the angle C. So we are going to state that the angle A plus the angle C is equal to 180, opposite angles of a cyclic quad. We know that angle C is equal to x plus 34. So we'll substitute that. From here, let us solve for A so we can use it in the next theorem. So it is going to be 180 minus 34 minus x. Therefore, angle A is equal to 146 minus x. So this is equation number 1. We are then going to take the value of A and substitute it into the next equation. So here, we are going to use the theorem that states the angle at the center, in this case it's angle O1, is 2 times the angle at the circumference, in this case the angle A. So those are the two angles we will be focusing on. So the angle O1 is equal to 2 times the angle A. Our reason is angle at center is 2 times the angle at the circumference. From here, let us substitute. So we know that the angle O1, let us just go and identify what is the angle O1. It is 4x plus 100. So we know that the angle O1 is 4x plus 100, and that is equal to 2a. Then we are going to substitute equation 1 into equation 2. Please take note that this is our equation 2. So here we have 4x plus 100 is equal to 2 times angle A, which is 146 minus x. We can then distribute into the bracket. We can move everything that has x to the left and everything that does not have x, so everything that is a constant, to the right. Please take note that when you move negative 2x to the left, it becomes positive 2x. So 4x plus 2x is 6x. When you move 100 to the right, it becomes negative 100. So 292 minus 100 is 192. We can divide both sides by x, and we therefore have x as equal to 32 degrees. So that is it. All we needed to do was identify which theorems to use or which theorems were present, and then connect them and solve for x. And that is it. In the diagram, O is the center of the larger circle. OB is a diameter of the smaller circle. So let's focus on that quickly. It is stated that OB is the diameter of the smaller circle. Please take note that a diameter will always subtend an angle of 90 degrees at the circumference. So anytime an angle is created or subtended by the diameter, it means that that angle is 90 degrees only if it is subtended at the circumference. If it is not subtended at the circumference, it is not 90 degrees. So here we now know that OMB is 90, and the reason is semicircle. Then it states chord AB of the larger circle intersects the smaller circle at M and B. So another thing to take a note of is theorem 1. So let's keep this 90 degrees. It is the line drawn from the center is perpendicular to the chord. So if the line drawn from the center is perpendicular to the chord, it then means that AM is equal to MB. And our reason is line drawn from center, perpendicular to chord. If that is the case, it means that the line drawn from the center has bisected the chord. Now, another important thing to take note of is that OB is not only a diameter, it is also a radius of the larger circle. Now that we've identified a few of the theorems that are present, let us have a look at the questions. Question 8.3.1, write down the size of OMB, provide a reason. So we've already discussed this. OMB is equal to 90 degrees. The reason is semicircle. It is because the diameter of the smaller circle OB subtends an angle of 90 degrees at the circumference of that smaller circle. So here, question 8.1. We are going to state that OMB is equal to 90 degrees, and our reason is semicircle. Next, let us have a look at question 8.3.2. If AB is equal to the square root of 300 units, so if you want to, you can put this into your calculator. So the square root of 300, that is equal to 10 the square root of 3. So if AB is equal to the square root of 300 units and OM is equal to 5 units, calculate, giving reasons, the length of OB. So first we need to go and identify what is OB. So OB is the diameter of the smaller circle, but it is also the radius of the larger circle. Now, we were given OM as 5 and we were given AB, so we can find MB. So we are going to use the radius of the larger circle, the side OM and MB, substitute it into our Pythagoras equation and solve for OB. So this is question 8.3.2. The information we are given is that AB is equal to 10 the root of 3. OM is equal to 5. Another important thing that is known is that this angle is 90 degrees, and that was proven in the previous question. Now, from here, let us start by finding MB. We know that MB is going to be a half of AB. So it is going to be a half of 10 the root of 3. It is going to be 5 the root of 3. Always remember that when the line drawn from the center is perpendicular to the chord, it means that the chord has been bisected, meaning it has been cut in half. So if you are given the length AB, all you do is half it, and you have the length AM or MB. So here, all we did was we halved 10 the root of 5. If you didn't want to convert it, you could have just put the square root of 300 and divided by 2 into your calculator. Now, the reason for this is the line drawn from the center is perpendicular to the chord. Now, we're going to focus on this triangle over here. Let us just write out the values. So we know that OM is 5. We know that MB is 5 the square root of 3. So we are going to write out our Pythagoras equation. It is the hypotenuse squared is equal to the sum of the squares of the other two sides. So OM squared plus MB squared, and that is Pyth. From here we substitute, so OB squared is equal to 5 squared plus 5 the root of 3 squared. We can put the entire right-hand side into our calculator, and that gives us 100. From here, we can square root both sides, and we therefore have OB as equal to 10, and that is it. All we needed to do was use Pythagoras to find OB. Take note that Pythagoras can only be used in a right-angled triangle. Next, we have question 9. Now, question 9 states, in the diagram, ABCD is a parallelogram. Please take note that the properties of a parallelogram is that the opposite sides are equal, the opposite sides are parallel, the opposite angles are equal, and the diagonals bisect each other. AB is 14, so because AB is 14, and we know that the properties of a parallelogram is that the opposite sides are equal, that means that AB is equal to DC is equal to 14. Then it states AD is produced to E such that AD to DE is equal to 4 is to 3. So we can write this as a fraction. AD over DE is equal to 4 over 3. So always remember, if the left is on top, the left number must also be on top. If the right side is at the bottom, the right number must also be at the bottom. We can also do the opposite. So we can say DE over AD is equal to 3 over 4. So we put the right side on top, which means we put the right number on top. We put the left side on the bottom, that means we put the left number on the bottom. So please take note of that. EB intersects DC in F, and EB is 21 units. So EB is this entire side over here that is 21 units. Now please take note that we have triangle EAB. Because DF is parallel to AB, it means we can use proportionality. We cannot use the midpoint theorem because ED is not equal to AD and EF is not equal to FB. The left and right sides of the triangle have not been bisected. If we were given that EF is equal to FB and ED is equal to DA, then it would be the midpoint theorem. Or if we were just given that one of the sides were bisected. So if we were just given that EF is equal to FB and we have parallel lines, then we could have used the midpoint theorem. However, we are not told that the left and right sides have been bisected. We are only given that DF is parallel to AB, therefore we can use proportionality on that triangle. Now question 9.1, calculate with reasons the length FB. So the length FB is this one over here. Please take note that we have the length EB and we also have the ratio AD over DE. So we are going to use the theorem of Pythagoras to find FB. So let us quickly sketch this triangle. So we have this triangle and it is called EAB. We have this parallel line. This is DC. Please take note that these two lines are parallel. Now from here we can use our proportionality theorem. Before we do that, let's make this a bit smaller so we have some space to work with. So it is known that AD over DE is equal to 4 over 3. It is also known that EB is equal to 21. Now, if you have a look at the ratio that was given, AD over DE, the ratio went from the bottom to the middle and then from the middle to the top. That is the ratio that they used. However, I am not going to use that particular ratio. What I'm going to do is I'm just going to fill in the information they gave us first. So they said that DE is in a ratio of 3. It doesn't mean the length DE is 3, it just means when you take the ratio of the bottom over the top, it is 3. And this bottom is 4. Doesn't mean the length is 4, it just means their ratios are 3 and 4. We then also know that the entire side EB is 21. So I am going to take the bottom to the middle and then the bottom to the top. The reason I'm going to do that, the reason I'm going to take the bottom to the middle is because that is what we are looking for. We are looking for FB. Before we continue, let me just double check my triangle because I think the C was supposed to be an F. Let us have a look. Yes, it is. It is supposed to be an F, not a C. So the reason I'm going to take bottom to middle is because we are looking for FB. And then I'm going to take bottom to top because we have the full length from the bottom to the top. So we are going to state bottom to middle and then bottom to top. So let's write that out quickly. It is going to be bottom to middle. So we'll say FB over bottom to top. So we'll call it EB is equal to exact same thing on the other side, bottom to middle, and then bottom to top. So it is going to be AD over DE. And our reason is proportionality theorem. And that is it. Now, from here, we are going to substitute. So FB, that is what we are looking for, it is going to remain FB over EB, that was given to us as 21, is equal to AD, the ratio of AD is 4, over EA, the ratio of EA is 4 plus 3, so it is going to be 7. Take note that because we are using the entire line, just add the ratios on that line. So it is going to be 3 plus 4, which is 7. From here, we can multiply both sides by 21, giving us 4 over 7 times 21. We can put this into our calculator, and we therefore have 12. So that is it. All we needed to do was identify that FB is a side on a triangle that we can use proportionality on. We identified a suitable ratio, substituted, and solved for FB. Next, let us have a look at question 9.2. Prove with reasons that triangle EDF is similar to triangle EAB. So please take note that when proving that two triangles are similar, we're going to prove that the first angle is equal to the first angle. So E is equal to E. The second angle is equal to the second angle. So D is equal to A. And the third angle is equal to the third angle. So F is equal to B. So let us quickly highlight the triangles we are working with. The first one is EDF. So triangle EDF is this one on top. Then we have triangle EAB. So triangle EAB is this larger one. Now, let us prove that they are similar. So we are going to state in triangle EDF and triangle EAB, the first angle is equal to the first angle. The second angle is equal to the second angle. And the third angle is equal to the third angle. So that's just the general setup. We need to go and be a bit more specific. Which angle E is it? Is it E1, E2, etc.? Which angle D and A and F and B is it? Is it D1, A2, F5, B3? We need to be a bit more specific. So let's go back to our triangle and identify which angle E it is. So as you can see, we don't have E1 or E2, it's just angle E. So let's just state E. Then let's have a look at D and A. So D in the red triangle is this one over here. It is EDF. So let's state EDF. That is the angle we are looking for. And angle A in the green triangle is this one over here. We can just call it angle A since it's on its own. Then angle F in the red triangle. This is the angle F in the red triangle. It is not the whole of F. It is just a small piece of it. So we are going to call it EFD. And lastly, angle B in the green triangle. It is not the whole of angle B, but a piece of it. So we are going to call it EBA. And those are our angles. Now, angle E is equal to angle E. That is common. Anytime two triangles share the same angle or the same line, the reason as to why they are equal is just because it is common. Now, let us go and identify why is EDF equal to A. So EDF, that is this angle over here. And angle A is this one over here. So why is EDF equal to A? You should notice the F shape. It is an upside down F shape. And when we are dealing with an F shape and parallel lines, our reason is corresponding angles. So the angle EDF is equal to the angle A, corresponding angles. Then we need to identify why is EFD equal to EBA. So this angle over here and this one over here. Once again, you should see the F shape, the upside down F shape. And we are dealing with parallel lines, so that means it is corresponding angles. And that is it. We've now proven that the two triangles are similar. So we can conclude to state, therefore, triangle EDF is similar to triangle EBA. The type of similarity is angle, angle, angle. You could have also put an A if you wanted to. You don't have to put the angle symbol. Now, Let's have a look at the last question, that is 9.3. Calculate with reasons the length of FC. So FC is this one over here. As you can see, FC is not within the triangle, it's on the parallelogram. Now, here we've already discussed that the opposite sides of a parallelogram are equal, meaning that DC is equal to 14 and DC is made up of DF plus FC, and we are looking for FC. So we can substitute 14 here. That means if we are able to find DF, we can then find FC. Because let's say, for example, DF is 4 as an example, right? Once you find DF, all you're going to do is substitute the value into this equation, and then you'll therefore have FC as 10. Take note that I don't know whether the value of DF is actually 4. It's just an example. So here we need to first find DF in order to find FC. So we need to ask ourselves now, how do we find DF? We can see that DF is a side on one of the triangles that we proved was similar in question 9.2. So that tells us that we can use those similar triangles to find DF. Always remember that if two triangles are similar, their sides are in proportion, meaning that we can formulate a three-prong equation and then take two of the sides that we need, or two of the parts that we need, and then solve for the unknown. So let us just erase this and then go and find DF so that we can find FC. So I'm going to recap what was mentioned one more time before we get started. So we know that one of the properties of a parallelogram is that opposite sides are equal. So that means that DC is equal to AB is equal to 14. And that is because the opposite sides of a parallelogram are equal. Now, we also know that the side DC is broken up into two pieces, DF and FC. So from there, we can create the equation DC is equal to DF plus FC. And we are looking for FC, and DC is known. So let us substitute DC as 14. Let us try to solve for FC. So we're going to get FC is equal to 14 minus DF. That means that if we are able to find DF, we will then be able to find FC. So to find FC, we first need to find DF. Now, if you remember what we previously mentioned, is that DF is a side on one of the similar triangles. So we can use the similar triangles to find DF. So that is it. We are going to use size in proportion of the two triangles we proved were similar to find DF. Once we find DF, we'll come back to this equation. FC equals 14 minus DF. Substitute DF, and we will then have FC. So let us try to find DF first. So we are going to use sides in proportion to find the length DF. The equation is going to be produced by taking the first two over the first two, the last two over the last two, the first and the last over the first and the last. What we mean by that is the first two letters of the name ED over the first two letters of the name EA. The last two letters of the name DF over the last two letters of the name AB. And finally, the first and the last letters EF over the first and the last letters EB. So that is it. Now, let us formulate this three-prong equation. As we mentioned earlier, it is going to be the first two letters over the first two letters, that being ED over EA. And that is equal to the last two letters, that being DF over the last two letters AB. And lastly, the first and last over the first and the last. Please take note that the reason we are able to create this three-prong equation is because triangle EDF is similar to triangle EAB. So that is going to be our reason. From here, we need to identify which two out of the three we are going to use. We are definitely going to use the second one, as we are looking for DF, and we have AB. It is known. It is 14. Then let us see between the first and the last, ED over EA and EF over EB. Which are we going to use? To identify which we are going to use, we need to identify which sides are known. If you remember from question 9.1, we determined the size of FB. We were also told that EB is 21. So we calculated FB as 12 and EB was given as 21. So if we want to find EF, we can take the length EB and subtract the length FB, therefore giving us the length EF. So we know that we can determine EF. And we know that EB is 21. So we are going to use the second and third. So here we have DF over AB is equal to EF over EB. We are going to substitute. So let's talk about how we are going to find EF. So we'll shift this to the left a little bit. Now, if we want to find EF, please take note that we were previously told that EB is 21. And we know that EB is broken up into two pieces, EF and FB. Let's just go back and confirm that. So here it is. You can see that the full length EB is broken up into EF and FB. So from here, we are just going to state EB is equal to EF plus FB, which was previously calculated as 12. So let us go and do that. So we're going to state 21 equals EF plus 12. Therefore, EF is equal to 21 minus 12, and that gives us 9. From here, we can substitute 9. We're then going to multiply by 14 on both sides. Alternatively, you can cross multiply. That is also acceptable. We can put this into our calculator, and we therefore have df as equal to 6 units. So we've now calculated df. Now that we have df, we can substitute this value of df into this original equation that we formed and then find fc. So let us just copy this equation. So we've just calculated df as 6. From here, we are going to substitute, and we therefore have fc as equal to 8. And that is it. In order to calculate fc, all you needed to do was identify that because you're dealing with a parallelogram, opposite sides of a parallelogram are equal, which means that AB is equal to DC is equal to 14. You know that DC is broken up into DF and FC. From there, you were able to create the equation. DC is equal to DF plus FC. We are looking for FC, so the only job was to go and find DF. We were able to find DF because we noticed that it was a side on one of the triangles that we proved were similar. From there, all we did was create our three-prong equation using size and proportion, solved for df, and then substituted it into this equation to find fc. And that is it. Next, let us have a look at question 10. Now, question 10 states, in the diagram, PQRS is a cyclic quadrilateral. So, P, Q, R, and S is a cyclic quadrilateral. And that means that the angle S4 and S5 plus the angle Q1 and Q2 is equal to 180. Opposite angles of a cyclic quad are supplementary. Then we can also state that P2 and 3 plus R2 and R3 is equal to 180. Opposite angles of a cyclic quad are supplementary. In addition to this, because this exterior angle can be produced, we know that the angle S3 is equal to the opposite interior angle. So S3 is equal to Q1 and Q2. We can also see that PQ subtends the angle S4 and the angle R3 at the circumference. So here it is going to be S4 is equal to R3. In addition to this, we can also see that the chord RS subtends the angle P2 and the angle Q1 at the circumference. So it is going to be P2 is equal to Q1. In addition to this, we can see that the chord RQ subtends the angle S5 and the angle P3 at the circumference. So S5 is equal to P3. And then we can also state that the chord PS subtends the angle R2 and the angle Q2 at the circumference. So we can then state R2 is equal to Q2. And all of this is due to angles in the same segment. The question further states such that PQ is equal to PR. So this is PR, this is PQ. If these two sides are equal, it then means that the angles opposite these sides, meaning R3 and Q1 and 2, would also be equal. So we can state R3 is equal to Q1 and Q2, angles opposite equal sides. The tangents to the circle through P and R meet QS produced at A. PS is produced to meet tangent AP at B. PS is produced to meet tangent AR at C. PR and QS intersect at M. So something important to take note of about the tangents is your tan chord theorem. There's actually a few of them. So the angle between the tangent CR and the chord SR, which is this angle R1, is equal to the angle in the alternate segment, which is P2. So here we can state R1 equals P2, and that is it. Then we can also use the same tangent CR and a different chord, the chord PR. And the angle between the tangent CR and the chord PR is R1 and R2. And this angle R1 and R2 is equal to the angle in the alternate segment, which is the angle Q, or you can call it Q1 and Q2. Then we can use our tan chord theorem on this tangent PB. So the tangent PB and the chord PR. The angle between the tangent and the chord is the angle P1 and P2. That is equal to the angle in the alternate segment, which is Q1 and Q2. In addition to this, take note that we can use the same tangent and a different chord, the chord PS, and the angle in the alternate segment will be Q2. So we know that Q2 is equal to P1 tan chord. In addition to this, because we know that tangent AR and tangent AP are from a common point, it means that the two tangents are equal to each other, and the reason is tangents from a common point. So we can state that AR is equal to AP, and because those two lines are equal, the angles opposite would also be equal, meaning that R1 and 2 is equal to P1 and 2. And that is it. So these are all the reasonings that I can see so far. So we are going to make use of most of them, if not all of them, when trying to calculate question 10.1, 10.2, and 10.3. Now, question 10.1 states, prove giving reasons that S4 is equal to S3. Now, please take note that when you are trying to prove that angles are equal, you're going to find out what is the first angle equal to on its own, what is the second angle equal to on its own, and then find a way to connect them. So we are going to find out what is S3 equal to. Then we are going to go and find out what is S4 equal to, and then try to connect them. So this is question 10.1. So I'm going to start with S3. The angle S3 is this one over here. So we need to identify what is the angle S3 equal to. So please take note that the angle S3 is the exterior angle of the cyclic quadrilateral. We spoke about that earlier. I think it was one of the first things that we discussed. So the exterior angle is equal to the opposite interior angle. That means that S3 is equal to Q1 and Q2. So here we are then going to state S3 is equal to Q1 plus Q2. The reason is exterior angle of cyclic quad equals opposite interior angle. Now, let us go and identify what is S4 equal to. So S4 is this angle over here. We need to identify what is the angle S4 equal to. So as you can see, the angle S4 is equal to the angle R3, angles in the same segment. The line PQ, or you could state the chord PQ, subtends the angle R3 and it subtends the angle S4. So here we are going to state that S4 is equal to R3, angles in the same segment. Now that we have what the angle S3 is equal to and what the angle S4 is equal to, let us find a way to connect them. If you remember in the information provided, it was stated that PQ is equal to PR, which means that the angles opposite those sides would be equal, meaning that the angle R3 would be equal to the angle Q1 and Q2. We previously discussed that. So because R3 is equal to Q1 and Q2, that means S4 would be equal to S3. So all we did was identify what are the angles equal to on their own and then try to connect them. So I'll show you where we discussed that. It was over here. R3 is equal to Q1 and Q2, if you remember. Reason is because PQ is equal to PR. So let us state this quickly. We are going to state that PQ is equal to PR. The reason is given. So because of this, we now know that the angle R3 is equal to the angle Q1 and Q2. The reason is angles opposite equal sides. So from here, because we know that S3 is equal to Q1 and Q2, and S4 is equal to R3, and R3 is equal to Q1 and Q2. We just discussed this over here. That therefore means that S3 is equal to S4. So here we are going to conclude, therefore S3 is equal to S4. And that is it. We have calculated question 10.1. We have proved that S3 is equal to S4. All you need to do is identify what are the angles equal to on their own and then find a way to connect them. Next, let us have a look at question 10.2. SMRC is a cyclic quadrilateral. So we need to prove that SMRC is a cyclic quad. So there are three conditions by which we can prove that something is a cyclic quad. The converse of angles in the same segment, the converse of opposite angles are supplementary, and the converse of the exterior angle equals the opposite interior angle. So here, let us have a look at this figure. We need to prove that SMRC is a cyclic quad. Now, if you notice, this has an exterior angle. It has this angle C1. If you can prove that C1 is equal to M1, that it is a cyclic quad. Alternatively, you can also use this exterior angle over here by S1. So if you can prove that S1 is equal to the opposite interior angle, R1 and 2, or you can call it CRM, then you have proved that it is a cyclic quad. Alternatively, you could use R4 and R3 and prove that that is equal to S6 and S5. We can also use S4 as the exterior angle and try to prove that it is equal to R1 and R2, or you can say CRM. Now, there's quite a few exterior angles to work with, so I'm going to proceed with that condition. If I can prove that the exterior angle is equal to the opposite interior angle, we will then have proved that the quad SMRC is a cyclic quad. Now, we've previously worked with the angle S4, so I'm going to use that one instead of the others that we spoke about. I'm using that because it's something that we've previously worked with, so we have a few built-up relationships regarding it, so it might be easier to use. So question 10.2, let us highlight this quad. It is SMRC. And please take note that it has the exterior angle by S4. So if we are able to prove that S4 is equal to R1 and 2, so let us try to make a note of this. We are trying to prove that S4 is equal to CRM, or you can call it R1 and R2. If we are able to prove this, then we will have proved that this is a cyclic quad. So in order to prove that S4 is equal to CRM, we are going to identify what is S4 equal to on its own and what is CRM equal to on its own. So I'm going to start with CRM because it's a new angle. We've not really worked with it before. We already know what S4 is equal to. S4 is equal to R3 and it is equal to S3 and it is equal to Q1 and Q2. So we already know what it is equal to. So let us try to start with R1 and 2, or you can call it CRM, and then we can do S4 later. So let us start by finding out what is CRM equal to. Now take note that the angle CRM is the angle between the tangent CR and the chord RP, and that angle CRM is equal to the angle in the alternate segment, angle Q, or you can call it Q1 and Q2. So here we can state that the angle CRM is equal to Q, the whole of angle Q, and our reason is tan chord. From here, we also know that the angle S3 is equal to the angle Q1 and 2, or you can say the angle Q. Reason being, exterior angle of cyclic quad equals opposite interior angle. Or we can just state proven because it was previously discussed in question 10.1. Then, in question 10.1, we previously discussed that the angle S3 is equal to the angle S4. And that was proven in question 10.1. So now that we know that S4 is equal to S3 and S3 is equal to the angle Q and Q is equal to the angle CRM, that means that the angle S4 is equal to the angle CRM. And we can therefore state SMRC is a cyclic quad. And our reason is the exterior angle of the cyclic quad is equal to the opposite interior angle. We'll first start by stating converse. And that is it. All we needed to do was identify what is the angle CRM equal to, identify what the angle S4 is equal to, and then connect them. And that is it. Lastly, we have question 10.3. RP is a tangent to the circle passing through PS and A at P. So we need to prove that RP is a tangent to the circle, and this circle is passing through P, S, and A, and the tangent and the circle touch at the point P. So first, let us go and make a circle passing through points P, S, and A. So this is the circle passing through the points P, S, and A. Then we were asked to prove that RP is a tangent to the circle at P. So this is RP. Now please take note that when proving that a line is a tangent, you can make use of one of three theorems: the converse of the tan chord theorem, tangent from a common point, or tangent perpendicular to radius. Now, we do not have tangents from a common point, nor do we know which is the radius of the circle, so we are going to proceed with tan chord. Now, if you notice, the angle between the tangent and the chord in the setup is P2, and the angle in the alternate segment is A2. So if we are able to prove that P2 is equal to A2, we will then prove that this is a tangent. So if PR is a tangent and PS is a chord, the angle between the tangent and the chord would then be this angle P2. The angle in the alternate segment would be A2. So if we are able to prove that P2 is equal to A2, we will then prove that this is a tangent. So to prove that PR is a tangent, we need to prove that P2 is equal to A2, and our reason will just be the converse of the tan chord theorem. So let's get started. If we need to prove that P2 is equal to A2, all we're going to do is identify what the angles are equal to on their own, and then try to connect them. Now, because we are going to be dealing with a lot of angles, it is going to make our life a bit easier if we allocate certain angles to be X and Y and Z, etc. We allocate them a variable. I'm going to start by looking for P2. When I'm done with P2, we will then look for A2 and then find some way to connect them. So here, so what is P2 equal to? Please take note that the chord SR subtends the angle P2 and the angle Q1 at the circumference. That means that Q1 is equal to P2. So we are going to state Q1 is equal to P2, and our reason is angles in the same segment. So we now know what P2 is equal to. It is equal to Q1. Now we need to identify what is the angle A2 equal to, and hopefully we can get it in terms of Q to somehow connect P2 and A2. So now let us try and find out how can we connect A2 to the angle P2. So please take note that we previously found P2 in terms of the angle Q, or we could say Q1. Now here we can also find A2 in terms of the angle Q. It's not Q1 like we found P2 to be equal to, but it is closely connected to Q1. It is the angle Q2. So I'm going to connect A2 to the angle Q2 by stating A2 plus Q2 is equal to P4. The exterior angle of triangle is equal to the sum of the opposite two interior angles. Now, we need to try and identify what can we get Q2 to be equal to. We now need to try to get Q2 and P4. We want to try to find them in terms of Q1 so we can connect A2 to P2. So let us find Q2 and P4. Now here, if you notice, the angle P4 is equal to the angle R3. The reason is tan chord. The reason I'm connecting the angle P4 to the angle R3 is because we know that PR is equal to PQ. It was given in the question, which means that if P4 is equal to R3 and R3 is equal to the whole of angle Q, we can then connect P4 to the angle Q like we wanted. So we are going to state that P4 is equal to R3. Our reason is tan chord. We also know that R3 is equal to Q1 and Q2. The reason is given. Now that we know what P4 is equal to, and we know what Q2 is equal to, we can now substitute them back into that original equation. So I'm just going to rearrange this so we can have Q2 as equal to R3 minus Q1. So we now have Q2 in terms of Q1, and we have P4 in terms of R3, so we know the R3s in both equations could possibly cancel each other out. So from here, we are going to substitute what our value of P4 is equal to and what our value of Q2 is equal to back into the original equation. Please take note that our goal is to try and find out what A2 is equal to and try to connect it to Q1 so that we can connect it to P2. So let's bring back our original equation. A2 plus Q2 is equal to P4. So we're going to state A2 plus Q2 is equal to P4. Now we don't need to put a reason because we're just continuing from a previous step. And if you remember, we stated that the angle P4 is equal to R3. And we stated that the angle Q2 is equal to R3 minus Q1. From here, we are going to substitute. So A2 plus Q2 is equal to R3 minus Q1. And P4 is equal to R3. From here, we are going to move everything that is not A2 to the left. So R3 minus R3 plus Q1. R3 minus R3 cancels each other out, and we are left with Q1. So we've now proved that A2 is equal to Q1 and that P2 is equal to Q1. So because of that, we can now connect A2 and P2. From here, we can therefore state, because we've proven that P2 is equal to A2, we can state PR is a tangent. And our reason is the converse of the tan chord theorem. And that is it. All we needed to do to prove that PR is a tangent is to use the converse of the tan chord theorem. We identified what P2 is equal to on its own, we identified what A2 was equal to on its own, and then connected them. If you felt like using the names of the angles was difficult, I would recommend using variables like x, y, and z. We could have made one of the angles equal to x and the other equal to y, for example, and then try to solve from there. So this is the November 2023 Euclidean geometry section.